Hello! Welcome to today's webinar, Tolerancing with QC Software for Color Consistency. Today, we will be discussing the various methods of color tolerancing and the importance of visual agreement in commercial printing and packaging. This is the third webinar of a six-part series designed to help print and packaging professionals tackle color accuracy. My name is Ed Hattenberger, Senior Color Scientist at X-Rite, and I will be leading today's session. Before we begin, if you have any questions throughout the presentation, please use the chat function to submit them, and I will do my best to answer as many as I can at the end. If we run out of time, an X-Rite team member will contact you afterward. So, let's get started. Color tolerancing can be done using a variety of methods. Agreement to visual standards is key, meaning are we seeing the same thing in our software that we are seeing during physical observation? So why not rely solely on visual inspection? Let's look at this example. Are the A and the B squares the same color? Do they look the same? A lot of people would say they are different. However, if we bridge these together and then mask the background design, you will notice that they are in fact the same color. But because of the surroundings, our eyes were fooled. There are a lot of factors that could trick our eyes, including retinal fatigue, background effects, like what we are seeing here, poor color memory, such as our inability to remember a color, color deficiency, lighting conditions such as fluorescent lighting versus daylight versus incandescent, age, and so on. Despite these challenges, use of visual guides remains an important tool, especially when shopping for products. While out shopping, if we notice a product looks faded or the color doesn't look quite right, it impacts our desirability to buy the product. When evaluating color, we use a variety of physical targets to judge accuracy. In production, this could be printed samples, ink drawdowns, or standardized color references. One example is the Light Standard Dark card, shown on the left side of the screen. This helps compare a target color to light and dark tolerance ranges. On the right, we have the Munsell Color Tolerance Set, which goes a step further by also showing shifts toward red, green, yellow, and blue. While these tools can be helpful visual guides, they do have limitations. For starters, physical targets need to be reproduced with extreme accuracy. Any variation makes them unreliable. They also have to be evaluated under consistent, controlled lighting, such as in a proper viewing booth. Another challenge? Color perception is subjective. What looks right to one person might seem off to another. And then there's durability. Over time, these physical samples can fade from light exposure, get contaminated by handling, or show wear like scuffs and scratches. But most importantly, they don't provide any numerical data. They just leave color evaluation up to interpretation, rather than giving an exact measurement of how far off a color really is. So we need numbers to understand the difference in colors. There's something called a color space that we use to measure differences between colors. Think of it like a three-dimensional map, where colors are plotted based on specific coordinates. Just like longitude, latitude, and altitude tell you exactly where you are on Earth, a color space uses three values to define where a color sits within a range. One of the most intuitive ways to describe color in this space is with the LCH model. The L stands for lightness, indicating how light or dark a color is, moving from black at the bottom to white at the top. The C stands for chroma, which tells us how vivid or dull a color appears. At the center of the model, you'll find neutral grays, and as you move outward, colors become more intense. Finally, the H stands for hue angle, which works like a position on a color wheel. It moves in a full 360-degree rotation to represent every possible hue. Another way to describe color within this same space is the L star A star B star model, or the C-Lab model, which is often shortened to LAB or simply Lab. Like LCH, L represents lightness, but instead of chroma and hue, we use two different axes to describe color shifts. The A-axis moves between green and red. Negative values shift toward green, while positive values move toward red. The B-axis moves between blue and yellow. Negative values are more blue, while positive values are more yellow. If both A and B are at 0, the color is perfectly neutral along the lightness axis. Now that we can precisely describe a color using these values, we also need a way to measure the difference between two colors. This is where delta E comes in. Delta E tells us how far apart two colors are in this space. First, we define the target color, our standard, by plotting its exact position in the color space. Then, delta E measures the distance between that standard and a sample color. The larger the delta E value, the greater the color difference. Tolerances determine how much variation is acceptable before a color is considered out of spec. Understanding these concepts helps ensure consistency and accuracy in color matching across different applications. There are a few different methods for tolerancing color differences. One of the most basic is the unweighted color difference method, where equal weighting is applied in all directions. This is the original delta E method, often referred to as delta EAB or delta E76, and it has been used for years to measure color differences, particularly in CMYK inks and process control in the press room. However, this method doesn't always align well with how we perceive color differences. In some cases, two colors may look significantly different to the human eye, but the numeric values suggest only a small difference, or vice versa. This can make it challenging to use for setting color tolerances in quality control. To address this issue, weighted color difference models were developed. These models assign different weightings to hue, chroma, and lightness to better match human perception of color differences. The idea is that when a color appears significantly different to the eye, the model should also reflect that difference numerically. One of the first widely used weighted models was delta E-CMC. Although delta E-CMC was once commonly used for spot inks and delta E76 for CMYK inks, delta E2000 is now the most widely used method for ensuring compliance in brand quality programs, applicable to both spot and CMYK inks, simplifying the industry's approach by eliminating the need to use multiple models for different types of colors. These weighted methods take into account the location of a color in color space and prioritize hue differences over chroma and lightness. This results in ellipsoid tolerance regions rather than simple spheres. Hue, which tends to be more noticeable to the human eye, is given a tighter tolerance, meaning less variation is allowed. In contrast, chroma and lightness are allowed to vary more. We are more sensitive to changes in colors with low saturation than to those with higher saturation. As a result, duller colors, such as those close to gray and pastels, have smaller ellipsoids with tighter tolerances, while more vibrant colors have larger ellipsoids, allowing for greater variation. There's also the concept of weighting factor specification. These tolerance methods include weighting factors that users can adjust to modify the shapes of ellipsoids, compensating for differences in perceived color variation. In the case of CMC tolerancing, the ratio is based on lightness, L, to chroma, C. Since the human eye tends to accept greater differences in lightness than in chroma, a common ratio used is 2:1. This means the tolerance allows for twice as much variation in lightness as in chroma. Occasionally, a 1:1 ratio is also used, but 2:1 is the most prevalent. With delta E2000, however, the mathematical model was designed to account for this ratio from the outset. Because of this, the default weighting factors follow a balanced 1:1 approach and are typically not modified. There are a few other tolerance methods used for specific applications. For those working with G7 for gray balance, this method involves adjusting the three primary color channels, cyan, magenta, and yellow to create a neutral, balanced gray with the proper tonality, while also fine-tuning the black ink tints to achieve the correct tonality. The G7 methodology uses delta L to measure the difference in lightness, excluding color, for assessing tonality, and uses delta CH to measure the difference in color, excluding lightness, for assessing color balance. In flexographic ink validation, the challenge lies in the wide variety of printing inks, substrates, and the specific properties inks must meet, such as food safety, scuff resistance, or fade resistance. A key focus is ensuring the ink color's hue angle matches the intended target. In these special cases, ISO specifications reference delta H sub AB, which assesses the hue angle of the ink, ensuring it aligns with a defined standard. With so many tolerancing methods available, choosing the right one depends on your specific application and ensuring clear communication. Here's what it boils down to. First, always communicate. Clearly document and share both the tolerancing method and the weighting factor with all parties involved. If these aren't aligned, there can be discrepancies in pass-fail decisions between printers and print buyers. Next, follow industry standards. Unless your print buyer specifies otherwise, delta E 2000 with 1:1:1 weighting is the standard to follow. This is where the industry is moving, supported by ISO standards and widely accepted by most customers and print buyers. Lastly, use customer-specified methods. If a print buyer requests a different tolerancing method or weighting factor, ensure that everyone in the workflow is using the same criteria to maintain consistency. When determining acceptable tolerances, it's essential to consider not just the method, but also the realistic expectations based on process capability. This is an agreement between the buyer and the print supplier, as some printing processes are more consistent than others. So as an example, many printing suppliers use tolerances like this, where they'll have a delta E 2000 as we described earlier. When targeting an industry print standard rather than their own press fingerprint data, the tolerance for CMY inks is typically up to 3.5 delta E, black ink may be up to 5 delta E, and spot inks generally have tighter tolerances, usually under 2 delta E. However, if the CMYK target values are based on their own press fingerprint data, the tolerances will be tighter for the process inks. In some cases, print conditions may necessitate larger tolerances. Factors such as the type of printing, substrate, printing press, and other variables can introduce additional variability into the production process. In these situations, a statistical assessment may be required to determine the expected variation of a well-controlled press under the desired print conditions. Statistical tools like an X-bar R chart shown on the screen can help assess production control. By measuring and evaluating data, you can identify points where the process is out of control, investigate the root causes, and determine whether the issue can be controlled. If it can be controlled, the tolerance remains unchanged. If it is inherent to the process and you can't control it, you may need to widen the tolerance to accommodate the natural variability of a well-controlled press. Ultimately, you may need to perform some of this work to determine the best tolerance target values for your specific printing conditions. It's crucial to document and communicate your color tolerances clearly across everyone involved in your workflow. To prevent miscommunication and errors, these tolerances should also be integrated into your color measurement process. For instance, if you're using an Exact2 without connected software, you can utilize Exact2 Suite to edit and configure tolerances within your color libraries before uploading them to the instrument. Once configured, the Exact2 will display an icon indicating pass or fail status, along with the corresponding delta E value for each measurement. In ColorCert QA tools. Software. There are several ways to configure your color tolerances. For example, you can set a global tolerance that applies to all your color standards for most production work. If a customer has specific tolerance requirements that differ from your standard production settings, you can add their name to the database, associate their colors with their customer name, and define their custom tolerances. Then, during production, selecting that customer's name will ensure that only their colors and corresponding tolerance values are available for measurement, streamlining the process and ensuring accurate compliance with their requirements. Some workflows require that all colors and print metrics be measured, validated, and reported. ColorCert press room tools and Measure Color software both include files that store predefined instructions for setting tolerances for each standard. For example, tolerances can be set at 3.5 delta E2000 for CMYK, 4.2 delta E2000 for overprint colors, and 2.0 delta E2000 for spot colors. These tolerances are embedded in the file and can be locked, ensuring that the press operator cannot modify the standard or its tolerance values. Now let's take a look at what to do when things go wrong. If you pass your tolerance checks but the customer still rejects the print, what can you do? First, ensure that everyone is assessing the color under the same parameters. In the print industry, lighting and illuminant specifications are standardized to D50. If people are viewing physical standards under different lighting conditions, or if their instruments are set to something other than D50, you won't get matching results. Next, make sure that all software and hardware are configured with the same settings. One common issue we hear about is mismatched values between software or devices. Often, this is due to different color settings, such as D50 versus D65, or using delta E2000 versus delta E CMC. You also need to ensure that the same type of instrument geometry is used. For example, a handheld Exact-2 spectrophotometer has very different internal geometry compared to a handheld or benchtop sphere device. The numbers from these different devices are not compatible with each other. Next, for non-opaque substrates, like certain papers or films, allow the backing material to show through. For example, if you measure on an ISO-compliant white backer and someone else measures on a sheet of white paper, you'll get different numbers. Ensure measurements are taken under the same conditions on the same type of material. Finally, consider whether the tolerances are realistic for the type of printing being done. Some processes are more variable than others, so you may need to adjust your tolerances accordingly. All right, let's take some time to address the questions submitted during the webinar. If you haven't sent in your question yet, feel free to use the chat function to do so now. I'll cover as many as possible, but if we don't get to yours today, an X-Rite color expert will follow up with you directly. Additionally, if you'd like to speak with someone about your specific color evaluation needs, a survey will appear right after the webinar concludes. All right, the first question we received is, my print supplier provided me with an ink proof that they said was under 1 delta E from my specified color. It looked great. Why would they need to have a 2 delta E tolerance on press? In the ink room, the technician has more control over variables like ink film thickness and ink strength when creating the ink proof. Since the proof is a one-off sample, it's easier to maintain precise color accuracy. However, on press, these variables can change throughout the run. Factors such as temperature, humidity, press speed, and even ink distribution can all affect color consistency. As a result, a slightly larger tolerance is necessary to account for these dynamic conditions during production. Usually, the ink room is held to half of the tolerance of the press room. The next question asks, why are the tolerance on CMYK inks usually larger than tolerances for spot ink colors? This is especially true when the CMYK ink color target values are based on established industry print standards like Gracol or Swap or Faux Gras, for instance. Your specific ink colors on your specific substrate will be a little different than those generic standards, and the CMYK ink colors are usually not modified, so the press operator has limited control of these colors. In contrast, spot ink colors are custom formulated, allowing for precise optimization to suit the specific print conditions, so they can be run with in tighter tolerances. Moving on to the next question. In this session, you spoke of color tolerances. What about dot gain or ink trap? Great question. Let's begin with ink trap. Ink trap refers to how two primary inks interact when printed over one another, which was traditionally used to analyze the overprints of red, green, and blue. In modern printing, standards specify target LAB values for these overprints. Since printing two inks together introduces additional variability, the tolerance is typically higher. For example, in most G7 workflows, the tolerance for overprints is generally set at 4.2 delta E. In the print standards, they now refer to dot gain as tone value increase, or TVI. This is not a measure of color. This is a measure of tonality. When printing to G7, TVI does not have any targets or tolerances for TVI. In Europe, FOGRA standards can have different target and tolerances based on the different print conditions. You should refer to your specific print standard for more guidance. The current versions of many print standards are preloaded in the Exact-2. ColorCert QA Tools supports only the color standards, ColorCert Pressroom Tools, and Measure Color supports TVI and other print metrics. All right, this is the last question I'll get to today. I understand that delta E can provide a pass or fail, but how can I determine how to correct the color? The Exact-2 and the QC software used during or after production don't directly identify the specific inks or pigments involved in the color, and delta E doesn't indicate the direction of the color error. However, you can gain valuable insights from the delta L, delta A, delta B, delta C, and delta H values. The largest delta points to the most significant color difference. For example, if the largest delta is in the L value, the issue is likely with lightness, which could be influenced by factors like ink density. A negative delta C indicates a color with a lower chroma, suggesting a potential ink strength or contamination issue, while a high positive delta A shows that the color is redder than the target. The Exact-2 in ColorCert features Best Match, while Measure Color includes ChromaTrack, which are both tools designed to help operators assess whether adjusting ink density or strength can bring a color within tolerance, or if they need to consult with their ink technician for correction. Okay, that concludes today's webinar. For those I didn't get to today, an X-Rite color expert will be in touch soon. Thanks again for everyone's time, and please stay on for a quick survey. Have a great day.